You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Edge AI refers to the practice of running artificial intelligence models directly on local devices, rather than sending data to the cloud for processing. In this model, the AI lives closer to where data is generated, such as on a smartphone, a camera, or a sensor. The term edge comes from edge computing, which contrasts with centralized cloud architectures by placing computation at the outer edges of the network. This local processing allows decisions to be made instantly, without the delays of transmitting information to distant servers. For example, a security camera equipped with Edge AI can detect unusual activity on site and trigger an alarm immediately, rather than relying on internet connectivity. For learners, the definition of Edge AI highlights a shift in where intelligence resides, no longer only in massive data centers, but increasingly embedded in the everyday devices we interact with. The Internet of Things, often shortened to IoT, describes the network of physical devices that are embedded with sensors, connectivity, and computing capabilities. These devices collect data from their environments, communicate with other systems, and often act on the information they gather. Examples range from smart thermostats that learn heating preferences to industrial machines equipped with vibration sensors to detect maintenance needs. IoT devices are distinguished by their ubiquity and diversity. They can be as small as a wearable fitness tracker or as large as a smart city traffic system. For learners, IoT represents the physical layer of connected intelligence. When combined with Edge AI, these devices do not just collect and transmit data, but also analyze and respond to it locally, creating a distributed web of smart objects shaping daily life and industry. The importance of combining Edge AI with IoT lies in the benefits it provides: reduced latency, improved privacy, and offline functionality. Reduced latency ensures that decisions happen in real time, which is crucial in safety-critical contexts such as autonomous driving or healthcare monitoring. Improved privacy results from keeping sensitive data local rather than transmitting it across networks, lowering exposure to interception or misuse. Offline functionality is another key advantage, allowing systems to operate even when internet connectivity is unstable or unavailable. For example, a voice assistant that processes commands locally can still function without relying on cloud servers. For learners, these benefits illustrate why Edge AI is becoming a strategic priority. It addresses the real-world limitations of cloud dependence while expanding the resilience and trustworthiness of intelligent systems. Hardware enablers have been central to making Edge AI practical. Specialized chips and processors, such as graphics processing units (GPUs), tensor processing units (TPUs), and dedicated neural processing units (NPUs), are optimized for running machine learning inference locally. These processors are designed to handle the repetitive matrix calculations required for deep learning, but in smaller, energy-efficient packages suitable for smartphones, drones, or embedded sensors. Hardware accelerators allow complex tasks like object recognition or speech processing to occur on devices with limited resources. For learners, hardware enablers demonstrate how advances in physical technology unlock new AI possibilities. Just as the spread of personal computers depended on accessible processors, the rise of Edge AI depends on compact, efficient chips that bring intelligence out of data centers and into the palm of a user's hand. Embedded machine learning is the practice of training AI models in central, powerful environments, but then deploying them on small, resource-constrained devices. Training a model requires large datasets and significant computing power, which is impractical on devices like wearables. Instead, training occurs in the cloud or on specialized servers, and the resulting model is optimized and transferred to the device. Once deployed, the device can perform inference-making predictions or classifications without sending data back to the cloud. For example, a smartwatch may not train its own heart rate prediction model, but can run an optimized version of it to monitor health trends continuously. For learners, embedded machine learning illustrates the complementary relationship between cloud and edge. The heavy lifting happens centrally, while the intelligence is delivered efficiently to where it is most useful. Real-time decision-making is one of the defining capabilities of edge AI. Unlike cloud-based systems, which require round trips of data to and from remote servers, edge systems can analyze information instantly. This is essential for contexts where delays could have serious consequences. In autonomous vehicles, for example, braking decisions must occur in milliseconds, too quickly to rely on cloud processing. Similarly, industrial robots on factory floors must detect anomalies and halt operations immediately to prevent damage or injury. Real-time processing at the edge ensures responsiveness and reliability. For learners, this concept underscores why edge AI is not simply a convenience, but a necessity in scenarios where immediacy determines safety, efficiency, and effectiveness. Speed is not just about performance, it is about trust in critical applications. Smart home applications showcase the everyday relevance of IoT and edge AI. Devices like thermostats learn user preferences and adjust heating or cooling automatically. Security systems equipped with cameras can detect motion, recognize familiar faces, and alert homeowners to intruders without constantly streaming video to the cloud. Appliances such as refrigerators can track contents and suggest recipes, while lighting systems adjust brightness and color based on time of day or mood. These systems often process data locally to preserve privacy and improve responsiveness. For learners, smart homes provide a relatable entry point into understanding edge AI. They show how intelligence embedded in familiar household objects enhances comfort, safety, and efficiency, illustrating the principle that AI is becoming woven into the fabric of daily life. Wearable devices represent another prominent category where edge AI and IoT intersect. Fitness trackers, smartwatches, and health monitors continuously gather data such as steps taken, heart rate, and sleep patterns. Many of these devices process information locally, providing immediate feedback like alerts for irregular heartbeats or reminders to move after prolonged inactivity. Advanced wearables are beginning to integrate predictive analytics, spotting health trends before they escalate into issues. For example, continuous glucose monitors combined with AI can help manage diabetes in real time. For learners, wearables highlight how edge AI moves beyond convenience into health and wellness, empowering individuals with insights drawn directly from their own bodies. They demonstrate the intimate, personal side of IoT, intelligence that lives not just in devices around us but on us. Autonomous vehicles depend heavily on edge AI to perform safety-critical tasks without reliance on the cloud. Cars equipped with sensors like cameras, LiDAR, and radar must interpret their surroundings instantly, from detecting pedestrians to recognizing traffic lights. Onboard AI systems process this sensor data locally, making split-second decisions about steering, braking, and acceleration. While cloud connectivity supports map updates or fleet coordination, immediate control requires edge intelligence. Without it, delays in data transmission could cause accidents. For learners, autonomous vehicles illustrate the most dramatic application of edge AI. Machines entrusted with human lives must think for themselves in real time. This example underscores why local intelligence is not optional but essential in domains where safety, trust, and reliability are paramount. Industrial IoT, often abbreviated as IIoT, brings together sensors and edge devices to monitor machinery, production lines, and supply chains. Sensors embedded in equipment track variables like vibration, temperature, or pressure, detecting anomalies that may signal maintenance needs. Edge AI processes this data locally, providing predictive maintenance alerts before breakdowns occur. This reduces downtime, improves efficiency, and saves costs in industries such as manufacturing, energy, and logistics. For example, an oil refinery might use IoT sensors combined with edge AI to prevent failures in pumps or valves. For learners, industrial IoT demonstrates how localized intelligence transforms not only consumer experiences but also the backbone of global infrastructure. It shows that Edge AI is not just about convenience, it is about resilience and efficiency at massive scale. Healthcare IoT is an especially impactful application, leveraging smart devices to monitor patients continuously and provide real-time support. Wearable heart monitors can detect arrhythmias and alert doctors instantly. Smart inhalers can track usage patterns, improving asthma management. Even implants, such as pacemakers, are increasingly designed with connectivity and local intelligence to adapt to patient needs. Edge processing in these contexts reduces latency, ensuring that alerts are issued immediately, while also preserving privacy by keeping sensitive health data local. For learners, Healthcare IoT illustrates the life-saving potential of Edge AI. It shows how intelligence at the point of care improves outcomes, empowers patients, and supports clinicians, while also raising important questions about security, trust, and regulation. In energy and utilities, IoT and Edge AI are transforming how infrastructure is managed. Smart grids use sensors to monitor electricity usage in real time, balancing loads and reducing waste. Edge devices detect outages or inefficiencies quickly, enabling faster response and predictive maintenance. Water systems employ IoT sensors to track flow and quality, reducing leaks and ensuring safety. These applications illustrate how Edge AI supports sustainability, optimizing resource use while reducing costs. For learners, energy applications demonstrate that AI is not confined to digital services but deeply embedded in the physical systems that power society. Edge intelligence enables infrastructure to be not just reactive but proactive, adapting to changing demand and conditions dynamically. Retail applications of Edge AI and IoT are reshaping customer experiences and operations. Smart shelves equipped with sensors can track inventory levels, automatically alerting staff or triggering restocking orders. Customer analytics tools use Edge AI to interpret foot traffic patterns, optimizing store layouts. Personalized promotions can be delivered in real time, informed by local data such as browsing behavior. Automated checkout systems use computer vision and IoT sensors to allow customers to walk out with items while purchases are tracked and billed seamlessly. For learners, retail provides a vivid example of how Edge AI translates into everyday convenience and business efficiency. It shows how intelligence embedded directly in the shopping environment improves both customer satisfaction and operational effectiveness. Despite its promise, Edge AI faces challenges. Devices often have limited processing power, storage, and battery life, constraining the complexity of models they can run. Designing models compact enough to fit on these devices without sacrificing accuracy requires advanced techniques like compression or pruning. Limited connectivity can also pose integration difficulties, especially in remote environments. Moreover, managing thousands or millions of devices at scale introduces logistical and technical hurdles. For learners, these challenges highlight that the future of Edge AI is not just about power, but about efficiency. Success requires creative strategies to fit intelligence into constrained environments, balancing ambition with the realities of hardware and energy limits. Security risks in IoT represent one of the most serious obstacles to widespread adoption. Connected devices are often vulnerable entry points for cyber attacks, as demonstrated by incidents where poorly secured IoT cameras or routers were hijacked into botnets. Edge devices processing sensitive data, such as health monitors or industrial sensors, face especially high stakes if compromised. Weak authentication, outdated firmware, and lack of encryption are common vulnerabilities. Addressing them requires robust security practices, including regular updates, strong identity management, and end-to-end encryption. For learners, IoT security highlights the interplay between intelligence and vulnerability. Embedding AI in the physical world expands opportunities but also increases attack surfaces. Trust in Edge AI depends not only on its functionality but also on the strength of the safeguards that protect it. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Data privacy is one of the strongest arguments for deploying AI at the edge. When processing occurs locally, sensitive information never needs to leave the device, reducing exposure to external servers or networks. For example, a smart speaker that interprets voice commands on-device can respond instantly without sending recordings to the cloud, protecting user conversations. Similarly, wearable health monitors that analyze heart rhythms locally preserve patient confidentiality while still alerting doctors to irregularities. This local-first approach builds trust, as users know their data remains closer to home. For learners, data privacy in Edge AI highlights how technology design intersects with ethics. It demonstrates that privacy is not only a matter of policy but of architecture. By choosing to process locally, developers can make systems inherently safer and more respectful of user rights. Edge intelligence therefore supports not just performance, but also the social acceptance of AI. Network efficiency is another key benefit of Edge AI, as local processing reduces the need to transmit massive amounts of raw data to the cloud. Consider a network of surveillance cameras. Instead of streaming all footage, Edge AI can filter out uneventful video and send only relevant clips for further review. This drastically reduces bandwidth consumption and lowers costs, while also easing pressure on central infrastructure. In industrial IoT, sensors may generate terabytes of data daily, yet edge devices summarize or compress results before transmission, ensuring that only actionable insights travel upstream. For learners, network efficiency illustrates the balance between local and central computing. By intelligently managing what data flows where, systems conserve resources while still providing the insights needed for decision-making. Edge AI thus transforms bandwidth from a bottleneck into an optimized pathway, ensuring scalability even as the number of connected devices continues to grow. Model compression techniques make it possible to run advanced AI models on devices with limited resources. Approaches such as pruning remove less important connections in neural networks, reducing size without greatly affecting accuracy. Quantization reduces the precision of calculations, shrinking memory and computation requirements. Knowledge distillation transfers learning from a large model into a smaller, more efficient version that fits on resource-constrained devices. These methods allow smartphones, wearables, and sensors to execute AI tasks once thought impossible outside data centers. For learners, model compression demonstrates the ingenuity required to adapt AI to the edge. It shows that progress is not only about building larger and more complex models, but also about refining them to be leaner and more efficient. This balance ensures that intelligence can be distributed widely, reaching even small devices embedded in everyday life. Federated learning offers a way to train models across decentralized devices without transferring sensitive data to a central server. In this approach, each device trains a model locally on its own data and sends only the learned parameters, not the raw information, back to a central system, where updates are aggregated. This technique is particularly powerful in contexts like healthcare or mobile personalization, where privacy is paramount. For example, smartphones might collectively train a predictive text model without ever sharing personal messages. Federated learning aligns the benefits of large-scale collaboration with the protections of local data sovereignty. For learners, it represents an innovative response to the tension between utility and privacy. It illustrates how AI can be both collective and private, ensuring that individuals contribute to global improvements without surrendering control of their personal information. Agriculture has become a fertile ground for Edge AI applications. Smart farming relies on IoT sensors and edge intelligence to monitor soil conditions, moisture levels, and crop health in real time. Drones equipped with Edge AI can scan fields for pests or disease, triggering immediate interventions. Livestock tracking systems analyze animal movement and behavior locally, alerting farmers to health concerns before they escalate. These tools help conserve resources, increase yields, and reduce environmental impact. For learners, agriculture demonstrates how AI at the edge is not limited to high-tech cities, but is transforming traditional industries. It highlights how intelligence embedded in fields and barns supports sustainability and food security, showing the global relevance of edge AI. From precision farming to animal welfare, the farm of the future is as much about data and devices as it is about soil and seed. Transportation systems are another domain where edge AI is critical. Beyond autonomous vehicles, smart traffic lights use local AI to adjust timing based on real-time conditions, easing congestion and reducing emissions. Fleet management systems integrate IoT sensors with edge analytics to monitor vehicle health, optimize routes, and ensure safety compliance. Public transit can leverage edge AI to provide predictive arrival times or detect overcrowding, improving service efficiency. For learners, transportation highlights the scale of impact edge AI can have on public infrastructure. It shows how localized intelligence in roads, vehicles, and logistics networks make cities more efficient and sustainable. Edge AI in transportation is not only about moving goods and people faster, but about designing mobility systems that are responsive, adaptive, and environmentally conscious. Public safety applications demonstrate the societal value of edge AI when deployed responsibly. Video analytics at the edge can detect unusual behavior in crowded places and trigger alerts for rapid response. Smart sensors in disaster zones monitor environmental conditions like smoke or seismic activity, enabling early warnings. Emergency response drones process video locally to assess damage and guide rescue teams. By providing real-time insights without relying on remote servers, edge AI ensures timely action when lives are at stake. For learners, public safety illustrates the urgency of edge intelligence. It also underscores the responsibility of ensuring these tools are not misused for excessive surveillance or control. The balance between safety and civil liberties is delicate, making ethical design as important as technical capability in public safety systems. Cross-device coordination is an emerging strength of IoT as networks of devices collaborate to achieve complex tasks. A smart home, for instance, may coordinate thermostats, lighting, and appliances to optimize energy use while maintaining comfort. In industrial settings, networks of machines synchronize production lines, adjusting dynamically to maintain flow and efficiency. Cross-device communication requires standardized protocols and intelligent orchestration, often managed by edge AI, that decides how devices share responsibilities. For learners, this highlights the shift from isolated smart gadgets to ecosystems of interconnected intelligence. Coordination magnifies the value of IoT, showing that systems become more than the sum of their parts when designed to collaborate. It reflects the principle of synergy, where distributed devices create outcomes no single machine could achieve alone. Cloud Edge Synergy describes the hybrid systems that balance local processing with centralized resources. While edge devices handle real-time inference, cloud systems manage training, long-term storage, and large-scale analytics. For example, an autonomous car may use onboard AI for immediate decisions, but upload driving data to the cloud for fleet-wide learning. In healthcare, wearable devices analyze daily signals locally but contribute anonymized patterns to cloud platforms for medical research. This dual approach combines the immediacy of the edge with the scale of the cloud, ensuring both responsiveness and continuous improvement. For learners, Cloud Edge Synergy illustrates that AI is not a zero-sum choice between local and central, but a dynamic partnership. The challenge lies in balancing which tasks belong where, optimizing systems for efficiency, safety, and adaptability across contexts. Energy efficiency strategies are critical for the viability of edge AI, as many devices operate on limited batteries. Designing lightweight models is one approach, but hardware optimization also plays a role. Chips are increasingly designed to minimize power use while maintaining performance. Dynamic power management techniques allow devices to shift into low-energy states when idle. Renewable energy sources, such as solar panels, are also being explored for powering remote IoT deployments in agriculture or environmental monitoring. For learners, energy efficiency shows how constraints drive innovation. It reminds us that building smarter devices means not only making them more capable, but also more sustainable. Energy-efficient design ensures that edge AI can scale globally without overwhelming power demands, aligning technical progress with environmental responsibility. Standards and interoperability are essential for the growth of IoT ecosystems. With countless manufacturers producing sensors, devices, and platforms, compatibility is not guaranteed. Standards ensure that devices can communicate and collaborate across vendors, enabling broader adoption and avoiding fragmentation. For instance, smart home appliances from different brands must work seamlessly together if they are to provide a unified user experience. Interoperability extends beyond technical convenience. It is also about security, as fragmented ecosystems may create vulnerabilities. For learners, standards highlight the importance of collaboration in innovation. AI at the edge cannot fulfill its potential if trapped in silos. Open, interoperable systems ensure that IoT networks scale smoothly and securely, benefiting individuals, organizations, and societies alike. Governance of IoT data is one of the most pressing concerns in this domain. Questions of ownership, compliance, and ethical use arise whenever devices collect and analyze information. Who owns the data from a smart pacemaker? The patient, the manufacturer, or the healthcare provider? How should data from smart cities be stored, shared, or anonymized? Governance frameworks address these questions by defining rights, responsibilities, and protections. Compliance with laws such as GDPR ensures that personal data is not misused, while ethical guidelines encourage transparency and fairness. For learners, governance illustrates the social dimension of edge AI. Technical progress alone cannot ensure trust. Clear policies and accountability must guide how data is managed. Responsible governance is the foundation of sustainable adoption, balancing innovation with rights and responsibilities. Scaling edge AI systems introduces unique challenges. Deploying millions of devices across cities, industries, or homes requires robust management tools, consistent updates, and coordinated security. Unlike cloud platforms, where central control simplifies operations, edge systems are highly distributed. Updating models or patching vulnerabilities across thousands of devices is complex and resource-intensive. Monitoring performance at scale also requires sophisticated orchestration, ensuring that systems function reliably across diverse conditions. For learners, scaling emphasizes that innovation is only the beginning. Real-world deployment demands logistical strategies and operational excellence, turning prototypes into resilient infrastructures. The future of edge AI depends not just on building smart devices, but on managing vast networks of them efficiently, securely, and sustainably. Case studies bring these concepts to life. In healthcare, wearable devices equipped with AI detect cardiac irregularities and alert doctors instantly, reducing hospitalizations. In retail, smart shelves equipped with IoT sensors prevent stockouts and enhance customer satisfaction. In manufacturing, predictive maintenance powered by edge AI reduces downtime and saves millions in costs. These successes are matched by challenges such as poorly secured IoT networks exploited in cyber attacks or devices failing under power constraints. For learners, case studies demonstrate that edge AI is not theoretical. It is already reshaping industries and daily experiences. They provide evidence of both potential and pitfalls, underscoring the importance of thoughtful, responsible design. The future of edge AI and IoT points toward more powerful, secure, and context-aware devices. Advances in hardware will continue to make local processing faster and more efficient, while federated learning and privacy-preserving techniques will strengthen trust. Greater interoperability will allow devices to work seamlessly across ecosystems, creating truly smart environments in homes, cities, and industries. At the same time, governance and ethical frameworks will evolve to address security, privacy, and equity concerns. For learners, the future highlights a broader vision: intelligence not confined to distant servers but embedded throughout the world, responding in real time to human needs. Edge AI and IoT together represent the frontier of distributed intelligence, transforming the way society interacts with technology at every scale, from the personal to the global. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.